Hello, Maurieo! In this video, Maurieo's trig levelling, that's trigonometrical levelling. We're going to look at trig levelling, or heighting as it's called. So, trigonometrical levelling, not as accurate as spirit or differential levelling, but it's great for high points not easily reached, and I use it quite a lot in topographical situations where we want to carry heights around a job but we don't need them to the accuracy that spirit or differential levelling is going to give us. Also, we can still do that, and then it gives us the opportunity to spirit or differential level at a later date if we need to. Now, in this diagram here, we show that the level line is a curved line parallel to the Earth, or mean sea level as it is here. And the level, if you set a level or theodolite at 0 degrees altitude or level, you can see that what you actually observe from the straight line is at a tangent to the level line, or the curved line that follows the curve of the Earth. So the target object appears level but is actually higher than the instrument by this little amount here, which is called the curvature and refraction. The curvature and refraction sort of, well, curvature in that case, but also refraction included in it. So let's have a little more detailed look at this. And the error sources in trigonometrical levelling are refraction. Now, refraction varies during the day. It's greatest at the morning and the evening. So the ideal time for observing is from 12 o'clock noon to around 3 p.m. around the middle of the day. Cloudy and overcast days are really good because they don't have an effect. And we should avoid grazing rays. Now, grazing ray is one where we perhaps get very close to the edge of the ground, or to the ground here, very close, and so that can be affected by the shimmer and the heat that's coming off the land, and changing the way the air that we are viewing through, changing the refraction. The coefficient of refraction is like I've set up here. With regard to that, the line of sight from the instrument is assumed to be a circular arc, but we actually look at tangential to that, and hence we end up with our curvature and refraction type things. But this coefficient of refraction. There are a number of methods of trigonometrical levelling. One is a single observation from one station with knowledge of the refraction coefficient, or the coefficient of refraction. So we have some ideas or knowledge about that refraction which we can apply to that single observation, which enables us to determine the difference in height with the forward mark, and if we have an absolute RL of the mark we're on, we can determine an RL for the forward mark. Another way of doing this levelling is using reciprocal observations. So in this case, observations are done from each end of a line in each direction. It is assumed, using this methodology, that refraction will be the same from each end of the line, and therefore it can be eliminated because it's observed in the opposite direction. It's worthwhile noting that refraction may in fact be least when shimmer is at its worst. So when it's very shimmery, sometimes a time when there's less, the refraction has less of an effect. Now, there is a third one which could be implied from the second, but I've isolated this out as a third option, and that's simultaneous reciprocal observations. This is when observations are done from each station at the end of the line at the same time. And this is not that easy to achieve because you are first of all observing, you need two instruments to observe from each end, one to the other, and it's quite sometimes quite difficult to actually, with people moving around the instrument and wearing high-vis jackets and what have you, quite difficult to actually get a very distinct point to observe. But that is the ideal one, is simultaneous reciprocal observations at the same time from each end of the line to two instruments. This one here is the next best, reciprocal observations, where you just observe from each end of the line, trying to keep the times of observation for each one very, very similar. Alright, so let's have a look at the single observation. But first, just a little reminder about how you might do this in a plane surveying situation, because the one follows on from the other. So for short distances, less than 200 metres, we take our observed line here and our horizontal, our vertical angle HA here, RL of A, HA, RL of B, HB, HB minus HA, our difference in height, and S, our distance, horizontal distance. So HB minus HA equals S tan HA, the vertical angle. So this is the actual vertical angle, not the zenith distance, as we might have dealt with in previous videos. In geodetic surveying, however, we're working over larger distances, and curvature and refraction become issues. So it can transpire that an observed angle of depression does not necessarily mean that the observed station is lower. So let's take a look at this diagram here. Here we have the line of sight here, but what we actually are looking at is a tangent to that, or what we're measuring is a tangent to that line of sight through here, and that gives us this little the angle of refraction, or what refraction is doing is this little angle here. So although we think we're seeing through here, we're actually observing here. So we need to actually allow or correct for this little angle here. So and we have also, if we take the verticals through the 2 points, they meet at the center of the earth and give us this angle here, theta. So the refraction angle, this one here, equals K, a constant, which we call the refraction constant, or coefficient of refraction, K, times this angle here, which is usually not much less than a second. Okay, much less than a second. Okay, so the ratio of the refraction angle to theta, the angle at the centre of the earth, is called the coefficient of refraction. And in New Zealand it's approximately 0.07 in New Zealand. So if we look here at the HT, or the difference in height, which is actually the height here is equal to HB minus HA, which is this here, the difference in height. Yep, HB, the height of B minus the height of A, that's equal to S tan HA, that's the angle we measure, and we gives us S tan HA, which is this little thing in here. Okay, plus curvature, which is as a result from curvature of the earth. So here's our what we perceive to be our horizontal here, but allowing for the curvature of the earth is this much here, which in here, minus refraction, and we put all that together into a combined correction, and we get S squared over 2R, which is our curvature correction, the distance squared over 2R, minus the refraction thing, which is the coefficient of refraction, times the distance squared over 2, and we put all that together and we get s squared equals 1 minus 2k all over 2r. Okay, and that is the combined curvature and refraction correction. Now from that we can work out how to apply the curvature and refraction just as a height correction. And here we have it here. By using that formula we can get C, which is just our curvature and refraction correction, equals plus 0.0673 times k squared in meters, where k is equal to the distance in kilometers. So it's always positive, and the correction is added algebraically with the sign to the vertical component, derived, and it's derived from the combined curvature and refraction formula. C equals s squared bracket 1 minus 2k all over 2r. So HB minus HA would then equal to S tan HA plus C plus the instrument height at A minus the target height at B. And we've got that all written there. So let's just have a look at an example. And here's an example. Curvature and refraction is a height correction. So there's our vertical angle, 42 seconds, instrument height, target height, RL of station A, horizontal distance, and let's curvature and refraction correction 0.0673 times 2.284, which is our distance in kilometers, squared, and that equals 0.3511. S tan 42 seconds equals minus 0.4651. Instrument height minus target height minus 0.06. Always be very careful that you get those correct and implied with the correct sign. And our RL at A, 354.26. Add all those together and we get an RL of our forward station B of 354.09. Now let's have a look using the same example of applying curvature and refraction as a correction to an angle. And in this case the formula would be HB minus HA equals S tan HA, our horizontal angle, 42 seconds, plus our correction, plus instrument height at A minus target height at B. And C in seconds is equal to S bracket 1 minus 2k over 2r arc 1 second. R is the radius of the Earth and K for New Zealand is 0.07. And putting that all together we get C equals 0.0139 S, where S is in meters. So using the same example, C equals 0.0139 S equals 0.0139 times 2.283.95. The distance is in meters this time, and that gives us 32 seconds. So let's now work out the difference in height. 2.283.95 times tan negative 42 seconds plus 32 seconds, which would be negative 10 seconds, and that's equal to minus 0.111. The IA minus TB is still equal to 0.06. Height of the station A, or the RL of station A, 354.26. So HB, or the RL of station B, the forward station, 354.09. So that correlates very well with the other method. And there you have it, two methods of applying the curvature and refraction correction. One as a correction to the height and the other as a correction to the angle. Now let's just have a look at reciprocal vertical angles. There's a number of possible alternatives here with the old reciprocal vertical angles. One is we can calculate the height difference from each end of the line without the curvature and refraction correction and mean them, and that's quite good. And the other one is to calculate from each end of the line with the curvature refraction correction and mean that, both give a pretty similar sort of result. The reason for the second one is that some instruments include the curvature and refraction correction and calculate height difference based on a constant, so it's easier just to sometimes record the difference in height as it comes out of our total station, rather than having to bother with recording our zenith distances and slope distances and what have you. However, in saying that, there are some very good reasons sometimes for collecting or writing down the zenith distance and the slope distance, because this enables, particularly if we're booking, not so much if we're doing digital collection of data, but if we're booking, because this gives us a check against writing down the wrong numbers, because we can always use the slope distance and the zenith distance to calculate out the differences in height and the horizontal values that we have written down out of the machine. It's a check against the other. So it is a way of doing that. So the two possible ways: calculate the difference from each end of the line without curvature and refraction, and this could mean, if you are using a total station, of zeroing the curvature and refraction constant that's in the machine, or we can do it with. Now let's have a look at a few errors that can occur when we're heighting. Systematic errors. These are the errors that we really need to look out for and try and minimize. So equipment out of calibration causes systematic error. If we don't use sufficiently accurate equations, we don't carry enough decimals forward, this can be a problem. Observer bias. If we observe some pillars differently to others because of the light conditions or their closeness or farness, this can cause a systematic error, and we've got to be very careful about that. Failure to apply corrections correctly can cause a systematic error. If we don't apply the slope correction, for instance, that can have a quite marked effect on things. And if we apply, say, a correction with the wrong sign or in the wrong direction, that can certainly cause some interesting systematic errors. And refraction itself is a systematic error. It's something that we can eliminate. Systematic errors are caused by physical and natural conditions that vary in accordance with known mathematical or physical laws. Gross errors caused by carelessness or confusion, misunderstanding and poor judgment. And some examples of these was get transposed figures, incorrect reading, misplaced decimal point, instrument out of level, changing constants mid-job, changing, if you're using a pole, changing the pole height and forgetting to do it, forgetting to change prism constants, things like this. Wrong point ID, if we identify the point incorrectly, and incorrect values for coordinates and heights. These can cause gross errors that can take a wee bit of finding. Random errors are personal reading errors, and these random errors usually mean to zero. These are errors that typically follow standard normal type of distribution, and so if you take enough measurements, they cancel one another out, and they mean to zero. So there you are, a little bit about trigonometrical heighting or levelling.